Hello everyone, so in this lecture video we're going to be talking about the types of chemical reaction, and we're actually going to be going through redox reactions or reduction oxidation reactions. So there are two, actually, even though it says three main types, there are actually two main types of chemical reaction. The first classification is actually called double replacement reactions. And how do you know it's a double replacement reaction, folks? Is what you do is you look at the reactants. The reactants are obviously on the left side of the yield arrow, and the products. If you look at this one, folks, this is a covalent compound. That's an ionic compound. You get another ionic compound, and you have another covalent compound. So you have compounds all the way across. So that means couples, 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 couples. And you can see that the hydrogen replaced the sodium here. H2O is actually can be written as HOH. Okay, and so we just replaced the Na with H, and then the H from Cl was replaced with sodium, and that's why it's called double replacement. This will be discussed in more detail later in the semester, so we're not going to talk about this too much, all right, for this part of the class. The second thing is the precipitation reaction, and precipitation reactions, folks, is you have something soluble in water, and you know it's soluble in water, by the way, by this, in this case, by this symbol called aqueous. Aqueous means solid dissolved in water. And at the end, what happens is, if you can look at this, we actually have something solid in water, and that's actually the solid in water is actually called precipitate, right? And so this, folks, FYI, comes from the application of solubility rules in your exam reference sheet, and I'm gonna get out of this one and just show you where that is very, very quickly. Okay, right? So if you look at your solubility rules here, so anything with sodium, potassium, lithium, all group 1 compounds, okay, anytime you see NaKLi, okay, it's soluble in water. That means all of these things that will have this is actually aqueous, okay? Everything that has all these ions are aqueous, right? Everything, if you have ammonium in front, like ammonium hydroxide, right, NH4OH, okay, that's soluble in water. NH4NO3, soluble in water. Okay, so again, all of those things are going to be soluble in water in this case, right? So that means it's also aqueous. All nitrates. So if you see NO3 at the end or acetates at the end, FYI, acetates can actually be written two different ways. And I'm just going to show you how acetate is actually done. Acetate can be written this way, or actually can be written as well as C2H3, right, O2. So this is also the acetate ion with a -1 charge. This is the same as CH3COO minus. C2H3O2 is also the same as that. So anytime you see that at the tail end of a compound, meaning they're ionic compounds, that is going to be soluble in water. It means it's going to be aqueous. It means it's going to split up in water. Okay. Now here's the exceptions. Now if you have chlorine, bromide, and iodide, so NaI, NaCl, NaBr, right? So NaI, those compounds are soluble in water. The only exception are three exceptions. If you see Ag in front of Cl, AgCl, PbCl2, Hg2Cl2, okay? If the positive ion are any of these three in front of these three negative ions, it's going to be insoluble in water. That means you're going to get, anytime you have this in front of this three, you're going to have something solid in water. Okay? Sulfates are soluble also in water. So anything that has SO4 at the end is soluble in water, except, just like number 4, if you have calcium in front, barium in front, or lead in front. Okay? So that's one of the few rules, and I hope that you guys can read through this, right? Because we don't really have a lot of time on this lecture. There are other exceptions to the rule. The other exception obviously is carbonates, all of these compounds. If you see CO3 as the negative ion, phosphate as the negative ion, sulfate as the negative ion, hydroxide as the negative ion, they're all solids in water, except if you have group 1, right? Group 1 Na, sodium, potassium, lithium in front, and ammonium in front. So if you have ammonium in front, even though it's a hydroxide, it's going to be soluble in water. If there's none of those 1 or 2, it's insoluble in water, meaning insoluble means it's a solid. Okay, and we're going to talk about number 7 when we talk about acids and bases. All right, so this is the rule that you need to understand for this case. Now, so that's where precipitation reactions occur. So you can actually predict a precipitation reaction just by looking at the actual products. So what happens is if you double displace, if one of the products is insoluble in water, insoluble actually means solid. It's not I, right? That means to say a reaction is going to occur. All right. So again, that is using the solubility rules in your exam reference sheet. And then we have oxidation reduction reactions, and there's actually in this case 4 different subtypes: combination, decomposition, single replacement, and combustion. And the reason we're going to talk about redox soon, and we're going to probably explain this by going through a problem, is because some of the species are going to lose and gain electrons. Okay, FYI, in a redox reaction, one species is always going to lose an electron, another species is always going to gain an electron. Okay, so you cannot have just someone losing an electron. You have to have this exchange of electrons in this case. Combination is you get 2 species and you end up with 1 species at the end. You have 1 species. The opposite of combination or synthesis is decomposition. You start with 1 species, you end up with 2 species, right? 2 individuals married, couple divorce. All right, worst analogy ever, but I'm going to use that anyway. Single replacement. Now, single replacement requires the use of your exam reference sheet again. Now, in this case, lithium is single and hydrogen is married to chlorine right now in hydrogen chloride or hydrochloric acid. Now, there's a possibility that lithium can knock out hydrogen from hydrochloric acid or not. How do we decide? We look at the activity series. Okay, and the activity series, I'm going to go back to the exam reference sheet, folks. Okay, is actually here. If the single atom is higher than the atom that is, in this case, married to the negative ion, if you look at it, here's lithium, here's hydrogen. In the previous example, right, hydrochloric acid, HCl, it was like this, right? And then you have lithium as the single guy. The question is, can lithium knock out hydrogen from chlorine? And the answer is yes. The reason why is because lithium is higher in activity than hydrogen. Now, what would have happened if we had H2 plus lithium chloride? In this case, there is no reaction. And the reason why there's no reaction is, as you can see, hydrogen is way lower than lithium. So again, the only way that a single replacement can occur is the single atom, the atom that's not combined with anyone, has to be higher than the atom that is combined with the negative ion. Okay, so I hope that makes sense. So going back to this balancing equation types of chemical reaction, so now we're going to talk about how can you tell physically again whether all of these things occur. I forgot to talk about combustion. Combustion, folks, is something's burned. You actually have a carbon plus oxygen, and you normally typically only have 2 products, carbon dioxide and water. For our purposes, that is the typical combustion reaction. Okay, there's other combustion reactions, but we're not going to worry about those things. So, all right, so there are rules for redox reaction and oxidation state. Oxidation states means to say that we're trying to monitor whether someone has lost or gained electrons. And it's probably better if we're going to go through an example right away. So we're going to do this example. And what happens, folks, is this whole thing has a charge of -2. One of the rules says that the oxidation state of oxygen when it's combined with anything else is actually -2. So I probably should use red, that way it looks better. -2, right? So there are 4 oxygens. 4 times -2, the total negative charge for this thing is, with oxygen, is -8. Now, the overall charge for chromium and oxygen is -2. So in order for me to get -2, the charge of chromium then has to be +6. Because +6 and -8 gives you -2. So that's the charge of chromium, +6. The charge of oxygen is -2, but the overall charge is -8. Aluminum, the charge of aluminum, anything that is not combined with anything else, has a charge of 0. All right? Then we go back to this rule. Oxygen has a charge of -2. Hydrogen has a charge of +1. That's one of the rules from oxidation states. 2 times 1 is +2. As you can see, the positive and negative numbers are equal. That's actually you have to balance that. Here we go. Chromium and hydroxide. So again, the charge, folks, of oxygen is -2. Okay. Oh boy, this is going to be very, very confusing here. The charge of chromium, we don't know. Now here, folks, the overall charge for this whole blob of things, okay, is going to be, in this case, negative charge, right? So the question is, what is the charge of chromium in this case? If I want to think about, and in fact, I think I already made a mistake. What's the charge of hydroxide, folks? The charge of hydroxide in this case is -1, right? So the question is, what is the charge of chromium in this case? So in this case, the charge of hydrogen is +1. Again, the charge of oxygen is -2. We need to have the overall charge of this thing to be just negative 1. -2 + 1, folks, is already equals to -1. So guess what the charge of chromium? The charge of chromium has to equal 0 in this case. All right. We're going to look at this again. Hydroxide again, and there's a 3 subscript. Okay, just as an FYI. This is +1 again. 3 times 1. I'm doing the hard way, folks, is +3. This is -2. Okay, 3 times 2 is -6. Right, -6 + 3. As you can see, this whole compound has no charge. We need to say it has a charge of 0. So you need to have equal numbers of negative and positive charges. So the charge of aluminum in this case has to be +3. And then again, this whole thing has a -1 charge. Hydrogen has a +1 charge. Oxygen has a -2 charge. And if you add those two things together, it looks like you have to have a -1 charge. Okay. Now we need to find out which species is being reduced and oxidized. So chromium, folks, went from +6 to 0. Okay. Right. That means to say when you become more, in this case, are you becoming more positive? You're becoming more negative. You are gaining electrons, so you are being reduced. Okay, so in this case, it's being reduced, and it has, if you look at it, it actually has, in this case, gained 6 electrons. If you look at it now, aluminum, folks, went from 0 to +3. So that means it has become more positive. That means you have lost electrons. So in this case, folks, aluminum is being oxidized. Okay, and it has lost 3 electrons if you look at it. Okay, FY, you don't really need to know, you only need to know 50% of this. All right, and all you have to think about this, folks, is once you find out one of them is being reduced, the other one that has changed charge is actually being oxidized. The most important thing here is, it's going to confuse you, keep going, is if you become more negative, that means you're gaining electrons. And the reason why you're gaining electrons is when you're becoming more negative is electrons are negative. Okay? When you're becoming more positive, you're losing electrons. And why are you becoming more positive? Because electrons are negative. So if you lose something negative, you become more positive in this case. FY again, if there's a species that is being reduced, there's also a species that being oxidized. Very, very important here. And I hope this little crash course in assigning oxidation numbers is helpful. A very, very confusing thing, folks. We're not going to talk about oxidation reducing agents because that's very confusing. It's actually the opposite. Whatever's being reduced is actually the oxidation agent. Okay. I know it's confusing. Just know this is just remembering nomenclature, and this is the reducing agent. Okay, so I hope that helps you figure out whether something is being, so in this case, because there's species that's being losing and gaining electrons, this is actually a redox reaction. Again, brief overview, 2 types of main reactions, double replacements, and redox reactions. And redox reactions has a variety of different reactions that has to apply multiple rules.